Okay. Hello, everyone. My name is Nathan Peck. I work as a senior developer advocate at Amazon Web Services. And today I'm here to talk about chaos. So, chaos is a pretty exciting topic. We got some chaotic noise back there too. I love that. So right now we're on a college campus. Obviously, there's a lot of first year software engineering students who learn about concepts of software engineering through something like the Turing machine. And the idea behind the Turing machine is it's obviously this theoretical machine that has infinite tape on either side and a read write, and it can calculate anything in the world. And it is an effective learning tool because it is chaos free. It always functions properly. It has infinite storage. It never makes mistakes. It never breaks. It's simple enough that you can understand it and understand the theory behind it and the theory of computing. But when you get out of the college environment into the real world of software development and building for the internet, real life ends up looking a little bit more like this. Obviously, I asked ChatGPT to draw a dramatized version of data center chaos. So hopefully, you have never seen a data center as chaotic as this. I certainly haven't, although I've seen close. Seen close. Yeah, I know, right? Now, take this image and let's look at another image which has some of the same energy, perhaps. This is Amazon Web Services. You saw in the previous fellow's talk, he showed the Uber microservices. Well, this is my turn to show Amazon microservices. You can see on 2008, that was the cluster of microservices that powered Amazon.com. And then on the right-hand side, you have in 2024, I captured this just a couple weeks ago. This is from one of our internal portals. This is the absolute galaxy of services connected together that power Amazon.com. Now, as you can probably imagine, this is incredibly complicated. There is stuff going on in all directions at all times of the day. And yes, there is chaos. I guarantee you at any given time, something is broken, somebody on call is getting paged, and there's some sort of disaster, right? And yet, the system as a whole functions pretty well. And how well? Well, here are some stats from Amazon Prime Day 2023. You may have seen these blog posts before. We publish a blog post every year from Prime Day about some of the service stats and things that happen on Amazon Web Services during that day of extra activity. And so you can see Amazon Elastic Block Store, which is essentially, virtual hard drives, 163 petabytes of data, 15.3 trillion requests at peak. You see Amazon Simple Queue Service, 86 million messages per second at peak. DynamoDB, 126 million requests per second. And Amazon CloudFront, which is sort of the web CDN in front of everything, 500 million requests per minute at peak and over 1 trillion requests total. So this is an incredible amount of scale that is being served by these systems inside Amazon Web Services in order to power a definitely non-trivial business built out of a lot of microservices. And it managed to stay online during this incredible burst of activity. So how is that possible? Well, it's from constantly fighting chaos. So for this section of the talk, I consider just going with something boring and just calling it like, you can't beat chaos or chaos always wins, right? But I decided instead to pick out a quote from one of my favorite philosophers, Alan Watts. He said something that I think is both optimistic and pessimistic at the same time. It's the ultimate glass half full, half empty. He says chaos is always losing, but it's never defeated. And so this is really what it is when you're building a large system. It isn't ever possible to completely defeat chaos, but if you do things right, chaos is always losing. So how does this work? Well, let's walk through some of the ideas behind chaos as being a spectrum. So if you think about building a stable software system at incredible scale, ideally you want as less of it as possible to be broken at any given time. So on the far end of absolute chaos, your entire application might be completely down. People try to load up the web browser and it just times out or spins forever and nothing ever loads up. On the far side of no chaos at all, the website loads up fast, loads up functions perfectly. That's the ideal, right? But in reality, your application is almost always going to be somewhere in between those two. Like some feature of the application may be slower timing out, some feature of the application may be broken. But if you build in a effective manner that can combat chaos, then you reach a point where you spend more time on that right-hand side and closer to that right-hand side than to the left-hand side. And one of the ways to do that is through redundancy. So I'm going to walk through sort of the scale of building out redundancy that I've seen throughout my career. The first one being the load-bearing laptop. Now, this is a very, very classic thing I've seen in startups. I worked at a startup that had a load-bearing laptop. Inevitably, there's some part of the business process which, of course, the CEO or somebody very high up in decision-making relies on, which is being powered by a laptop that sits on somebody's desk, right? And so what happens is that employee goes on vacation, the laptop turns off, or something happens to the laptop. Next thing you know, emails are being sent by the CEO. What's happening to that important report that I expect to receive every day on my email, right? So this is a high chaos system. This is a system that's very vulnerable to chaos because this part of the business is being powered off a personal laptop. Any number of different things could happen to that laptop. Coffee could spill on it. It could be powered off. Cleaners could unplug it by accident. So how do we move up the ranks and get a little bit further away from that chaos? Well, here's the next tier, the IT closet. All right, this is a classic one I've also seen. Hopefully, you've never seen IT closet quite this dusty, but yeah, once again, I've seen close. So let's get that application off of a personal laptop. Let's get it onto a server that sits in the closet somewhere, and that server is going to be plugged in to internet and power and running nonstop, right? And this functions pretty well usually, but it depends a lot on how important the business is to you and the value of your data. Because I start to wonder, this server that's sitting in the closet, what happens if the electricity goes out or the internet goes out here at the office? And it's not an uncommon thing for that to happen. And then how often is this thing getting cleaned? What if that dust does build up? The thing starts to overheat, and next thing you know, your website's slow or some business process is failing because of that hardware failure. So as the business grows and becomes more valuable, the data behind the business becomes more valuable, we start to move to another tier, perhaps the co-location facility. So this is a classic one. You have a bunch of server racks in a facility. Usually you'll have cages around them, so that way, people can't mess with each other's hardware, some physical security there. But the facility will probably offer redundant power, internet connections. There's a variety of protections that you get from hosting your application on a server out of a co-location facility that you're not going to get running it in the IT closet at your office. But there's still problems that can happen. Famously, I think it was like last year or the year before, one of these facilities caught fire in Europe. I'm not going to call them out by name because it was very embarrassing, obviously for the entire industry. The fire suppression system failed. Every single server went up in flames. Countless amounts of user data and business data was lost forever in that fire. So this is still a little bit scary. If my application data is stored in one physical location in a co-location facility in one part of the world, if I lose that server in that co-location facility, my entire business could also be gone. So here we get to Amazon Web Services. Obviously, I work for Amazon Web Services. I'm going to pitch the cloud. And cloud, what is a cloud deployment? Well, a cloud deployment is really the idea that your application data are not hosted in one specific location. They're replicated. So they're replicated across multiple redundant pieces of hardware in multiple locations. When you see an AWS region, let's say like US East 1, US East 2, US West, or whatever, what this is made up of is different availability zones, which are each their own physical buildings with their own redundant power and internet, their own redundant fire suppression systems, and they're separated by distance, in some cases up to 50 miles. We don't want them too far apart, because if they're too far apart, now you have some speed of light latency between these facilities. But we want them far enough apart that you can be fairly confident that a disaster could occur at one of these facilities and not have an impact on the others. So ideally, let's say like a forest fire sweeps through, or God forbid, a nuclear bomb drops in one area and a particular facility is destroyed, you could actually have your data in your application replicated to other facilities, other availability zones within that region, and you can actually survive that chaotic event. So this feels pretty strong. This feels like it's very resilient to chaos, and it is. I think right now there are some people who are pushing back against the cloud because they say the cloud is a little bit expensive. They say, I would like to go back to a co-location facility, or I'd like to go back to the IT closet in my personal office because it'll be a little bit cheaper, right? And it's very interesting because there are proponents and opponents to that idea. There are some people who say the cloud is much cheaper than on-prem, and there are some people who say on-prem is cheaper than the cloud. So how is this possible? How can there be two conflicting ideas? And what I've come to realize is it comes down to what you are comparing against. It's not an apples-to-apples comparison always. When you are looking at a co-location facility or you're looking at the IT closet in your office, you're talking about a single location which is vulnerable to forms of chaos that could completely eliminate your business and all of its data in one fell swoop. Whereas when you're talking about the cloud, you're talking about a distributed system where your data is actually replicated across an extensive distance. And there's a significant amount of redundancy in the operation of that system. So for a small startup to be able to create that level of resilience and redundancy would be extremely expensive, to have 2, maybe 3 facilities that they're hosting their application across, compared to, maybe one facility that is their on-premise or co-location facility. So really what you're comparing is a singular deployment to this distributed deployment. Now, as I mentioned before, this deployment seems very resilient to chaos, right? And it is. It's resilient to a lot of forms of chaos, but it's not completely resilient. Like we said earlier, chaos, we're always fighting it, but it's never defeated. So what's the type of chaos that can hit this? Well, this is a classic one that's happened. It's happened to AWS regions before. Someone digging with a backhoe hits a network cable. And while I've never actually worked in the backhoe industry, my understanding is that there is a term for this, and it's kind of scary to think that there's a colloquial term among backhoe drivers that when they hit the network cable, they call it digging up the rainbow root. So yeah, imagine you're digging with the backhoe, up comes the rainbow root. Well, somebody in IT is having a bad day. Suddenly some of those AWS regions are disconnected from each other. Some applications, some data isn't syncing. Maybe the data is in one different state in one data center than it is in the other data center. This is kind of bad, and it happens more often than you think. So this highlights a paradox of resiliency. And the paradox is that the more distributed your system is, the more resilient you are against certain forms of localized failure. A nuclear bomb could drop on one availability zone of an AWS region, and it wouldn't actually take out your data in another region or another availability zone. But when I have this distributed system, it means there's more independent pieces that can fail, and it means there's more connectivity dependencies. So if I lose connectivity and the connectivity fails between some of these distributed pieces, that makes my entire system a little bit more vulnerable to that sort of coordination and syncing that needs to happen for everything to function smoothly. So how do we solve this problem, right? We're still trying to fight that chaos. We don't want to succumb to chaos. We want to be resilient. Well, I'm going to bust out another Alan Watts quote. He says, the more a thing tends to be permanent, the more it tends to be lifeless. And the last thing we want is your website or API to be lifeless, right? We want it to be online at all times. So how does this apply? We want to embrace impermanence. We want to embrace ephemeral computing. So what does this mean? It means that when I am treating my computing as ephemeral, none of my servers are special. They aren't pets. They're just capacity. You've probably heard the term before. The server is a cattle, not pet. And more than that, if I have racks and racks of servers, I could power any of them off at any time. I could cut the network cable to it. I could do whatever I want. I could physically destroy one of those servers, and your application keeps functioning. Randomly, we could go in and unplug or kill a piece of hardware, and the thing continues to work. So how is this possible, right? Well, containers are one of the solutions that enable ephemerality. Traditionally, with applications that run on a single host, you have this dependency between the application and the host because you need to make sure that you run the application on a host that has all your dependencies. Let's say it's a Node.js application. Your application has to run on a server that has Node.js installed, the right version of Node.js. It has to have the npm packages installed. Maybe it relies on certain operating system packages that are on that host. But containers say, let's take all of those dependencies, let's decouple them from the underlying host, and let's package them up into what we call a container image. And the idea behind that container image is that you can use it as a basis to describe a deployment that can be deployed onto any host, and any server can be used as raw compute capacity to run an application container. So here's an example with Amazon Elastic Container Service, which is the team that I work for. Obviously, Kubernetes is another option as an orchestrator. But at a high level, I create a description of my application, such as I have a container image here. It needs 1 CPU and 2 gigabytes of memory, and I want to launch 4 copies of it as a distributed service. And so the orchestrator is treating all of this hardware as raw capacity that it can place your application onto, and the capacity is dumb. I can remove any of it anytime. Here's how that works. So here is an example of 3 EC2 instances. These are VMs, which roughly map to the underlying hardware inside of a AWS data center. And you can see that they're running a few different components now. They're running Docker or Containerd, and they're running an orchestration agent, which lives on that host and makes that host something that can be controllable by an external orchestrator. The external orchestrator is going to launch containers on that host. So these containers don't necessarily have to have a one-to-one mapping. This is one of the common mistakes that I see of people adopting containerized technology. They say, well, how do I match my container to the size of my host? Or how do I ensure that my container is using the entire capacity of the host? Well, you don't. The idea is you start from the container and you define what the container needs. In this case, let's say 1 CPU. And if that server has 4 CPU cores and your application only needs 1 CPU, that means you can run 4 copies of the application on that server. It's not a one-to-one, it's a one-to-many ratio there. Now, the orchestrator not only is launching things on these hosts, but it's also watching over the application's containers that it launches to maintain availability. And so different chaotic events can happen. So let's say the code inside your container crashes, it has a runtime exception. The entire container ends suddenly and abruptly. The orchestrator is going to notice that application container disappeared, and it's going to reboot it. And it may reboot it onto the same host, or it may reboot it onto an entirely different host. Now, likewise with the VM, let's say I talked earlier about the idea that I could unplug one of those servers, I could cut the network cable, I could physically destroy the hardware for one of those servers, and my application continues running. Well, how is that possible? The orchestrator is watching, and when it sees that the EC2 instance as a whole is terminated or disappeared, it's going to know what was on that host, and it's going to relaunch replacements onto different hosts inside the AWS data center. So this allows me to survive a hardware failure, an unexpected hardware failure, and the lifecycle of my application is no longer tied to any specific piece of hardware. Now, the existence of the application is not the only part of the story. The other part of the story is my application actually functioning correctly? So an orchestrator has health probes. And the idea behind a health probe is I can investigate or introspect the application to see whether it's behaving as intended. And this is most often useful with something that's like a web or an API service, where I want to know, is my application actually responding with 200 status code, 200 OK status code, or is it responding with a 500 status code that indicates server-side failure? Is it timing out? There are different, or is it just not accepting requests at all? There's a number of different scenarios that can happen with a web-facing workload where I can notice from outside of the machine that this container is not behaving as expected. And if it's not behaving as expected, I can terminate it and launch a replacement on a different host. There's also the capability to run a health check inside of the container. So this is nice because the agent is already running there on the same hardware as your application container. And so we know that it has a connection. It's not going from outside of the host. It's right there inside of the host. And so it can run an arbitrary command that you specify inside of your application container, and that the response from that command will indicate whether or not that container is healthy. So that can also be a health probe. Now, the last part of this story is shifting web traffic. So obviously, I'm describing a pretty dynamic system where application containers could be on any host. They could move to any other host whenever they become unhealthy. how does this work for like a web-facing workload? Well, obviously we need a way to redirect the web traffic. You know, when people hit mycompany.com in the browser, they always want to see my company website, even if the IP addresses and location of the application is changing dynamically behind the scenes. And so the way we accomplish that with an orchestrator is, for example, on AWS, we have the concept of the application load balancer. Application load balancer has a built-in resource called a target group, which is a list of targets that the load balancer will send traffic to. And the orchestrator keeps that list of targets in sync. Even as containers crash, restart, they get stopped, they scale down, they scale up. It's constantly keeping that target group in sync whenever there's a change to the state of the containers or even the location of the containers on a different host or a different server. And it also even goes to the extent of draining traffic safely whenever it's stopping a container. So we know that a container is about to be stopped, perhaps because of part of a scaling in process. Well, what we can do is we can adjust the load balancer to stop sending new traffic to that particular target, wait for any traffic that's currently in flight to that target to finish being served, and then shut down the container. So that way you get zero downtime. You're not going to be dropping requests as part of scaling in or adjusting the number of containers that you're running. So here's the map of chaos reduction that I've discussed so far. You know, obviously there's the hardware infrastructure, which we're going to solve with redundancy. We're not going to use a load-bearing laptop. We're going to have, you know, multiple copies of the application distributed, running across different physical locations. We have the software deployment, which we're going to solve with ephemerality and orchestration. You know, rather than having the lifecycle of the application tied to specific hardware, an external orchestrator is going to launch the application on any arbitrary piece of hardware that we provide as just dumb capacity. Now, the last part, though, is the code implementation. And here be dragons and obviously many bugs. Like, it's hard to get developers to write code that is 100% chaos free. I know that I certainly can't. You know, if I'm trying to write code, I guarantee you there's going to be some bugs, there's going to be some problems in that code. So how do you reduce that level of chaos? Well, once again, I'm going to pull out another quote. Henry Ford. This is one of my favorite quotes from him. He said, "The only real mistake is the one from which we learn nothing." So mistakes in code are inevitable. It's kind of hard, and especially as people, you know, embrace like large language models to write code, that code's also going to have bugs in it. So these mistakes are inevitable. They can't necessarily always be avoided, but we can learn from them. So the idea behind chaos engineering is that it should be a flywheel, right? We start out the system with a steady state, and we form a hypothesis about what might happen in my software system if this particular chaotic event happens, such as a network cable being chopped up by a backhoe. Then we run an experiment. The running of the experiment triggers or simulates this particular condition. We verify what the behavior of the system is. If necessary, we make an improvement and then run another experiment. But the idea is, as this flywheel turns, each time it turns, the software system as a whole gets more resilient. You get better error handling. The most common form of failure that people have is that when they're building a distributed system, they assume that the network connection between two components is always going to be up, and they don't do a proper error handling to say what happens if this particular request that I'm making from one microservice to another service times out, or what happens if it fails. Do I need to retry it? It's extremely easy to miss. Everybody does it. I've done it. You know, you just fire up a request and you assume that it's gonna work. So this is the number one thing you're gonna find with this flywheel is every single place where there's a missing error handling for component to component communications. So these experiments are run through a process of intentional fault injection, and there's different ways to do it. The sort of classic way to do it was something that was introduced by Netflix called Chaos Monkey. And this is an open source tool that triggers and simulates different types of errors. AWS offers AWS Fault Injection Simulator. And the idea is you're going to use it to inject different types of faults, such as network traffic black hole, traffic latency. So there's a delay between traffic traveling between two components. Packet loss, network partitions, where one part of the network is disconnected from another part. And also resource saturation. Let's say I completely run out of CPU and memory, or even sudden hardware failure. I can trigger turning off any piece of hardware at any given time. So the idea behind this is, as I run these fault injection scenarios, I go from it being a mystery to being, I've seen this before. Ideally, when you encounter an error or a failure, you don't want it to be something where you can spend all night trying to debug it. You want it to be something that you have seen before because you deliberately triggered that failure. And because you triggered that failure, you know what it feels like, you know what it looks like, you know what the logs look like, and you recognize that and can act on it similar to how you've solved that problem before. And part of how you solve that problem, especially in a larger organization, is you write a correction of error document. So the idea behind this document is you write up what happened and what was the impact. And what were the root causes? Notice I didn't say root cause, I said root causes. Oftentimes there are multiple root causes that contribute to a particular failure. And one way to explore that is to keep asking why. Why did this happen? And then why did the cause for that happen? And why did the cause for that happen at least 5 times? What data do you have to support this? Did you dig through logs and find an error in the logs? Did you look at a particular graph of a metric? What lessons did you learn from this failure that you discovered? And then what corrective actions are you taking? And the idea is that this document serves everyone on your team and potentially everybody in your broader organization so that they can learn from a particular chaotic event that happened as part of your infrastructure. And it's very important to make sure this is a healthy culture. So when you write a correction of error document, it's not as punishment. It's not, oh, Nathan, you made this terrible error, this terrible bug that hit production. You need to write a correction of error document because you messed up. No, the idea is that I write that document because I want to improve, and I want everyone else to improve and learn from my mistake. And they learn by sharing that correction of error document widely across the organization. Ideally, though, also the learnings from that document get codified as mitigations that can be applied later. So automated guardrails like limits and checks that happen during your runtime build process and release process to ensure that a particular error doesn't happen again. Like if you can build a linter rule, if you can build some sort of static code analysis to detect this particular type of failure, you can prevent it from happening again. So I'm going to close out one more quote. This one, she's not a philosopher. She's actually a child specialist. But I really like this quote from a book that I was reading recently about raising children. She said, "Do not be dismayed by the brokenness of the world. All things break and all things can be mended, not with time, as they say, but with intention." And I find that this is so important because it's the same thing. Everybody's code is broken. I've worked at startups where the code is broken. I work at Amazon where the code is broken. Nothing is ever 100% unbroken, but you can mend it with intentional action. And here's the intention here. Hardware infrastructure can be solved with redundancy and distribution. Software deployments with ephemerality and orchestration. Code implementations can be improved through fault injection experiments and a correction of error culture. So thank you very much for attending this talk. I think we are out of time, but I may be able to take a couple of questions or questions asynchronously because I think it is already 5:04.
Would you mind going back to that last slide?
Yes. There you go. And if you want to reach out, I have my Twitter handle and email address are there as well. Thank you very much for attending this talk, and I hope you learned something and were mildly entertained.